Hi, folks. This time let's talk a little bit about solubility. And solubility is defined as the ability of one substance to dissolve another. And the general rule in chemistry is like dissolves like. Now, what does that mean? Well, we've been talking about organic versus inorganic compounds, and that's going to give you a big hint about what we're talking about. But let's talk about this like dissolves like and solubility thing for a minute before we go there. You know that oil and water do not mix. You've probably had enough salad dressing that you know sometimes you have to shake it up really well before you stir it in order to get a good mixture of the two. But when we're talking about solubility in chemistry, you have to have the right solvent in order to clean whatever you're trying to clean. If you're working in the shop and your hands are full of oil and grease and muck, and you try and hit them with plain water, you're not going to get clean. So you have to have the right cleaner. You might use Gojo or lava soap or something else that is really going to work well on that oil and grease. If you have a part or a carburetor or something else that really have to be cleaned, you've got to pick the right solvent, whether that be acetone or MEK, methylethyl ketone, or something else. You've got to find the right solvent. So chemically, what do we mean by this like dissolves like? This goes back to organic versus inorganic molecules, and they're constructed differently. Organic molecules tend to be what we refer to as non-polar. And inorganic molecules tend to be polar. Now, chemistry is this huge topic, and I'm simplifying it down to the very basics. So there are 100 exceptions to this rule. So, if you know of an exception, good. There's probably lots of them. But this is the basics here. What do I mean by polar and non-polar? Well, if you think of the Earth and its magnetic field, there is a north and a south, and it's like there is a magnetic pole inside of it. And there is one end versus another end to that magnetic field. That's what we mean by polar. If a molecule is polar, it has two different ends, and the two different ends are different. When we're talking about molecules, we mean they are electrically different. We mean that the electrons tend to hang out on one side more than another. If we're talking about a non-polar molecule, we mean a molecule that is pretty symmetrical all the way around. So I've provided some pictures to help illustrate this. If we're talking about an organic molecule, this one is propane, the same sort of propane that you would use in a gas grill. And a propane molecule is pretty much the same from all sides. It is one end doesn't look any different than the other end. Octane, which is one of the molecules you're going to find in gasoline. This end looks pretty much like that end. Organic molecules tend to have very similar structures all the way around. They also have a tendency to be kind of greasy and slippery. So if you're talking about fuel for a car or a heating system or a boat or a ship or whatever, Vaseline versus cooking oil, they tend to have this kind of a shape. Inorganic molecules, if you're talking about rocks or mountains or water, tend to be non-symmetrical. One end's different from another. And here is a diagram of a water molecule. Water molecules are very polar. And what that means is because it's two hydrogens and one oxygen, oxygen is an electron hog. It has a strong affinity for the electrons, so lots of the electrons tend to hang around by the oxygen, and it leaves the front end of the water molecule very negative, and the back end of the water molecule very positive. And this non-symmetry gives it different properties when you try to dissolve things. Salt, table salt, plain old ordinary salt you put on French fries, is also polar. Salt is one sodium, one chlorine atom. Sodium is a big molecule. Chlorine tends to attract more electrons than the sodium, and so this end tends to be very negative, this end tends to be very positive. And when you construct a salt molecule, these little positives and negatives just kind of line up like little soldiers in a row, and they make nice square crystalline shapes. These crystalline shapes can get so big that if you allow these large crystals to grow, you can actually see this tiny microscopic structure reproduced large if you let the crystals grow big enough, which I think is absolutely cool. So if we talk about like dissolves like and solubility, there is a range of this. There are multiple different kinds of solvents, and organic substances tend to dissolve organic substances, and inorganic substances tend to dissolve inorganic substances. This is a big deal. Put a star by it. That's something I really want you to understand. So if you've got hydrocarbons, they are going to be good at dissolving other hydrocarbons. If you've got a spot or a stain that is made of grease and you want to get that out, well, you're going to be better with something like acetone and lighter fluid and things like that. These molecules are very nonpolar and they are very symmetrical. If you've got something that's a little different, well, then you can get molecules that are not quite as symmetrical, and you can get into ether or MEK, methyl ethyl ketone. These molecules can dissolve things, a variety of things beyond just pure grease, because they have some slight nonpolar properties to them. On the other end, you've got that strong polarity of water. One end's really negative, one end's really positive, and that's going to dissolve those really polar things. In the middle, you've got something like alcohol. Alcohol, and we're talking about the same kind of alcohol that a person would drink, like ethanol. One end here is a little different. Everything here looks pretty symmetrical, but it's got a little different end down there, so it's a little bit polar. And then there's the big dissolver, carbon tetrachloride. Carbon tetrachloride is a super duper dissolver. The challenge with carbon tetrachloride, it is a huge, massive cancer causer. And some industries still use carbon tetrachloride because it is fabulous at dissolving grease and oil. It is a carbon molecule surrounded by 4 chlorines. The challenge with that is these chlorines are so strong at pulling at other electrons and causing chemical reactions, is that they can cause damage to biological systems. So most people who handle carbon tetrachloride have to have special training and licenses to do so. Let's talk about water as a universal solvent. That's one of the things that you will hear. Water is referred to as a universal solvent. Now, is that 100% true? No, because you all know water is not great at dissolving grease. But look at the massive amount of things that water is good at dissolving. I think one of the best pieces of evidence for water being a super duper dissolver is the Grand Canyon. If you've ever seen pictures of it or you've had the honor of going there, there is this huge damaging hole in the earth, and it was caused by nothing but the erosion of water and time. Water can dissolve salt and all sorts of salts and minerals. Alcohol and water are 100% miscible, it's called. It's kind of close to the word mixable, but it's called miscible. We use water to wash everything from our dishes to our cars to our bodies because water is so good at dissolving other things. And again, it's down to the fact that one end is very different than the other, and it will pull dirt and other chemicals away. But if you've got something that is greasy and has got a lot of organic dirt on it, you are going to need something to bridge the gap between the oil and dirt and water. And then you need our superhero, our superhero soap. Soap is a magnificent molecule because what soap does is soap bridges the gap between oil and dirt and water. This is a stylized, simplified soap molecule. There are many different kinds of soaps and detergents, but this is the basic structure. A soap molecule is going to have 2 ends. One end is called hydrophobic, or it is an organic end. This end likes oil and fat. The other end is hydrophilic, or water-loving, and this is an ionic end, and this end loves water. So what happens is, oil and water don't mix. Soap goes in, has a handshake, it combines with the water, it combines with the oil and dirt, and when you pull the plug on the sink, it is going to go down the sink with the oil and the water, and it is going to take the oil and grease with it. Because we all know when we wash our clothes, our cars, and our bodies, a rinse off with water will get some dirt off, but you got to throw some soap in there if you want things to be really good and clean. Now, soap does something else, and it's in this broad category of chemicals called surfactants. They actually make three-dimensional structures, which are called micelles. And this is kind of cool because if you've ever washed dishes by hand, you've seen these in action and maybe not even known this is happening. A little soap molecule can be stylized this way. This is the little organic end, and this is the little end that likes water. This is the water-loving or hydrophilic end. What happens is if you've got a little bundle here of dirt or oil or grease, what will happen is the little soap molecules will line up. Well, that's just one. What happens is the soap molecules absolutely encapsulate the entire water, grease, and oil. And that little encapsulated bundle is called a micelle. So there used to be an old commercial for Dawn dishwashing liquid that said, Dawn takes the grease out of your way. And it does, because it would encapsulate the grease and the oil. So when you pulled the plug on the dishes, down the drain, the grease and oil would go. I don't know if it's ever happened to you, but like on Christmas, Thanksgiving, when I'm washing a lot of dishes, I would get to the point where the suds would be gone. And I'm going, where did all the suds go? Well, all the soap molecules were used encapsulating all the goop and the grease and the oil. And if that's happening, well, just go for it. Put more soap in or change the water. The water's probably gross and icky at that point in time. All right, that's going to do it for solubility, and we'll see you later. Bye-bye.